Hi guys, Ms. Zimmer here with our last portion of Radicals for this year, Radicals Part 3. The beginning of this lesson actually starts with adding and subtracting radicals. We just did that in Part 2. So when you start your homework, you can use that information from Radicals Part 2 to continue. We're going to go ahead and move on to multiplication in Radicals Part 3. So, how would we handle multiplying the square root of 3 and the square root of 7? Well, earlier we might have had to break down the square root of 24 to simplify it, and we broke it down into the square root of 4 times root 6 and made it 2 root 6. So what are we doing here? We're going backwards. Instead of breaking it down, we're multiplying it. And yes, you would get the square root of 21. The one thing you have to ask yourself is, can 21 be simplified? The answer to that question, no, it cannot be simplified. No perfect square goes into 21, so that one is complete. Now, what if we multiply a radical by itself? Well, if you multiply a radical by itself, you're always going to get a perfect square, because that is the definition of a square. When you take 3 times 3, you get a perfect square. 4 times 4, you get a perfect square. So a radical times itself will give you a perfect square. So we can cut straight to the chase and just say the square root of 3 times square root of 3 is 3. Next, what if we have the square root of 5 times root 15? Well, you've got a couple of ways to look at this. You can either multiply it together and then say, is there a perfect square there? Yes, the square root of 9 times root 5, so my answer is 3 root 5. Or you can do this. You can break down 15 into root 3 times root 5. Recognize that root 3 times root 3 is 3. Root 5 is left, and again get the same answer, 3 root 5. So there are a couple of different methods for breaking down roots or multiplying them. You can multiply them outright and simplify, or you can break them apart into similar roots if you find that convenient. Next one. Two root 3 and 5 root 2. Luckily, unlike addition and subtraction, our roots do not have to be the same to multiply or to divide. Now here, we have a number in front of our radical, sort of like our coefficient. So 2 times 5 would be 10. Root 3 times root 2 would be root 6. And we ask ourselves the question, can 6 be simplified? No, it cannot. So that is our answer. Next one, what if we have radicals? Well, we can multiply everything that's underneath the radical. 2 times 6 gives us 12. X to the third times x gives us x to the fourth. Just like when we multiply radicals with, variables without radicals, we would add the exponents. We'll still do that rule. Now, 12 can be simplified. That's the square root of 4 times the square root of 3. Plus, we also have x to the fourth underneath, and there's an index of 2. 4 divided by 2 gives us an exponent of 2. So we have a 2 here, the square root of 4. We also have an x squared here with no radical sign left. So we have 2x squared. The square root of 3 is the only part that cannot be simplified in that, or is not a perfect square. So 2x squared root 3 would be our answer there. All right. Here's a few other types of multiplication you can see. Let's try 3 root 2 squared, or 2 root 7 squared. Well, 3 root 2 squared means that we're multiplying 3 root 2 by itself. 3 times 3 is 9. Root 2 times root 2 is 2, because a root times itself is the number, it's because it's a perfect square. And we get 18 for our answer to 3 root 2 squared. So what's essentially happening is 3 squared is 9, and root 2 squared is 2. So it functions almost like a power of a power. Everything inside gets that same power. So 2 squared is 4, and root 7 squared is 7. So the answer here would be 28, multiplying that together. All right, what about cubes? Keep in mind, you can multiply if numbers have the same index. If they don't have the same index, watch out. So here we have 4 and 18, so we can go to our little trusty calculator and say, hey, what's 4 times 18? It's 72. So that would be the cube root of 72, 4 times 18. Well, let's think about our cubes. 8 is on our cube list. This is the cube root of 8 times the cube root of 9. We have to find that cube root and put it in front of the cube root of 9. If 9 was a square root, we could find a square root, but there is no cube root to 9. So this would be our final answer. That turns into a 2, but that's not, there's no cube root to 9. All right, here's another one with a cube root. Cube root of 10 times a cube root of 50 gives us a cube root of 60. Well, 2 cubed is 8. 8 does not go into 60. 3 cubed is 27. 27 does not go into 60. 4 cubed is 48. For some reason, I keep remembering 4 cubed. 4 cubed is 64. 64 does not go into 60. So we cannot simplify this one at all. Yes, there are a lot of other numbers that go into 6, but there are no cubes that go into 6. Not 8, not 27, not 64, or all out of cubes that might possibly go in there. All right, next up. Oh, I just made a big boo-boo. I just added these together. I am so sorry. You're probably thinking, what is she doing? My apology. 50 times 10 is 500. I'm glad my brain caught up with me. So now let's go back to our cubes. We do have 5 cubed is 125. So is 500 divisible by 125? Well, yes, it is. And what goes in? 4. So we can break that down into cube root of 125 times the cube root. It goes in 4 times. So this turns into a 5, because the cube root, the 5 cubed is 125, and the cube root of 4 stays right where it is. So luckily I came to my senses on that one. I don't know why I forgot and added underneath the radical. Silly me, because we never do that. So don't do it. Okay. All right, next up, we are going to continue multiplying, but we get to multiply binomials. Yay! So you get to FOIL again, but now with radicals. I know you're super excited about that. All right, so let's start by distributing to a binomial first, and then we'll get to FOILing with the 1. So let's call this A and this B. so we can tell they're two separate problems. All right, so let's just do a little distribution. When we're distributing, we know that the number in front of the parentheses gets distributed to everything inside. So root 5 times root 5 minus root 5 times root 2. We know root 5 times root 5 is the square root of 25, which is 5. And 5 times 2 is 10. Thank goodness I didn't add again. And there's our answer. You're like, can't we subtract these? No, we cannot, not without turning them into decimals. And the one thing that we will not do anywhere in our radical problems is turn these into decimals, because we're in simplifying and working with them in exact form. Now the next one, let's multiply this out. The square root of 3x times x, and the square root of 3x times 5 root 3. In the front, we have a square root of x times the square root of x. Well, anything times itself under a radical, that's an x value. So you can think of this as square root of 3 square root of x separate. These two together gives us that x. The square root of 3 stays behind. Here we have a root 3 times a root x. So the root 3 times root 3 is 3. We have a 5 times 5, and the root x stays right where it is. So yes, this is 15. Remember, we can't touch this subtraction until all of that multiplication is completed. Order of operations. Okay. All right, so now we have x root 3 minus 15 root x. And we're finished. Again, they don't have the same root, so we cannot add or subtract them. So that's the end of that one. Okay, I promised you doing some foiling, so let's do that next. Distributing done. So let's start with C, the square root of x plus root 2 square root of 3 minus root 2. So let's go ahead and FOIL. First, the square root of x times the square root of 3 is the square root of 3x. First, outer. Excuse me. Getting tired here, sorry about that. Outer minus positive times negative is negative, square root of 2x. Inner, root 2 times root 3 is root 6, positive. And then last, root 2 times negative root 2 is negative 2, because the root 2 times root 2 is 2. Now, we don't have any other like terms, just checking. Oh, that's it. All complete, no like terms. Well done. Next one up. This one will have some like terms, you'll like it much better. Root 5 minus 7. This is A in the next example, and root 5 plus 7. Now save a simmer. Is that like the conjugates when you had x minus 7 and x plus 7 and they were conjugates? Yes, but they work a little bit differently here. Root 5 times root 5 firsts gives you a 5. Outer, root 5 times 7 gives you plus 7 root 5. Inner gives you minus 7 root 5. So the conjugates, these middles are going to cancel each other out again. And last, negative 7 and positive 7 minus 49 when we multiply those together. These are going to cancel, and we get 5 minus 49 is negative 44. So when we have conjugates with radicals, all the radicals disappeared. Okay, yay! So that you'll be able to tell when you're doing those correctly. Okay, let's try another one. Sometimes people think this is a conjugate, but it's not. We have the square root of 7 in the examples. Square root of 7x, the x is underneath it. Square root of 7x plus 2 squared. So it looks like it might be a conjugate, but it's not. Conjugates, one's positive, one's negative. So I would highly recommend that you write it twice before you FOIL, so you don't make any errors there. Write it twice and then do firsts. Well, if it's the same, it's just 7x, no radical. First outer plus 2 root 7x. Inner plus 2 root 7x. So this is going to end up being a trinomial. Okay. Remember, when you have something of this form, the outer and inner end up being exactly the same. And last plus 4. So when you combine these like terms in the middle, 7x plus 4, square root of 7x plus 4. Is your final answer no like terms, or no like radicals? All right, follow those rules for a radical homework part 3, and you can go back to the last video if you need some help with the adding and subtracting, which is at the beginning of radicals part 3. Good luck.